Hello everyone, my name's Aaron, and here we are on Leetcode, and today I thought we could have a look at the daily challenge, which is the game of life. So let's have a quick read of the instructions here. The game of life is, this John Conway's game of life. So the idea is that a cell is either alive or dead, and effectively it depends on itself and its neighbors to determine whether it is going to stay alive or dead in the next round. So, 4 rules. Any cell with fewer than 2 live neighbors dies as if caused by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies as if by overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. The next state is created by applying the above rules simultaneously to every cell in the current state, where births and deaths occur simultaneously. Given the current state of the n by n grid board, return the next state. Okay. Does it have rules about what happens at the edges? Doesn't say, so I'll assume it's a torus. That is something on the edge. We'll wrap around. So this one here, for example, this one has just 1, 2, 3, 4 live neighbors. So in the next round, it should be dead, but it's alive. What? Maybe this counts as just 3 live neighbors. Okay. All right, so we have the current board, which is a grid filled with numbers. What we can do is effectively have a second board that we're going to count the neighbors of each cell in. This is an empty array. Let's just get the size of the board, just so we know how big a cell we're working with here, how big a board we're working with, so we can iterate over this thing a little more easily. So let's do a bit of a loop here. The idea is we're going to start at the top left, and what we're going to do is we're going to look at every cell. So the neighbor counts, we'll create a neighbor row that we're going to build up as we go. So what we want to do is, into this particular cell, we want to create a neighbor count. So the neighbor count of index ij is effectively all of I minus 1, I plus 1, j minus 1, j plus 1. Let's work out the neighbor count. This is going to be the board. Because these are zeros and ones, it's just a sum effectively. Neighbor board I minus 1, j minus 1, board I minus 1, j. Now the trick is going to be if any of these are, if I or j are the extremes of the board. I have forgotten what exactly JavaScript does in this particular case. Hopefully something sensible. Oh my goodness, this would be so much easier in something like APL. Which of course is quite famous for solving the game of life very tidily. In fact, you know what I'll do? JavaScript really needs to get itself some list comprehensions, because this would be so much tidier if I had them. In fact, I should be doing this in Python. So neighbor count. Actually, let's check this. If in fact, even better, let's actually have these range over the right things. If I plus dx is less than 0, or I plus dx is greater than equal to this isn't dx at all, it's di. That's not going to go. This is dj. If I plus di is less than 0, or I plus di is greater than the number of columns, no, rows, or j plus dj is less than 0, or j plus dj is greater than or equal to the number of columns, do nothing. So really we should invert that particular condition, but I cannot be bothered. Neighbor count. Oops, I don't need to do a layer on that. That's all the wrong key bindings here. All right, so that now gets us the number of neighbors of each cell. But this is one too high because we've added up 9 cells. So we need to just take off the current value. Right, so now we know how many, oh god, that's a lot of code for a very simple question. How many neighbors does each cell currently have? So now we want to go through and do quite a lot of this again. 0, I plus rows, I plus for j, so now we know how many neighbors are currently alive, so now we just need to encode the rules. If neighbor counts, and put that in parentheses, if neighbor counts of I and j is less than 2, the board I, j is going to die. Else if neighbor counts I, j equals 2. Hang on. These are only the rules for a live cell. So it's if board I, j is currently equal to what's currently alive, these are the rules we want to follow. So 1, 2, 3. What the heck is going on with this? There we go. If we'll come back to that. So if it's alive and fewer than 2, if it's alive then equals to 2, or neighbor counts I is 3, it lives on. Else more than 3, that's just the else condition. it dies. Board I j equals 0. Otherwise, if it was dead, if neighbor was dead, and now it's going to become alive, exactly 3 cells. We have resurrected the board. That's mutation board. The next state is given by applying given the current state of the board, which in the next state. Oh god, was I meant to create a new board? Oh, do not return anything. Modify the board in place instead. Okay. So we are in theory on the right track. Let's have a quick skim through and see if we've done the right thing. In fact, you know what we're going to do? I think this all can be its own function. This gives us a nice separation of concern. That way we can focus on just the bit we're interested in here, which is the neighbor counts. Down here we want to go the neighbor counts is count neighbors of the board. Let's assume for a second that works fine. And then we want to go through every cell. If the cell is currently alive, then we apply these 3 rules here. If the neighbor counts is less than 2, it dies. In fact, we can simplify this logic quite a bit. The neighbor counts is greater than 3, it also dies. And then all of this logic can go away, because in the 2 or 3 case, nothing happens, it just carries on. So now that's nice and simplified. And then in this case here, if the neighbor counts is exactly equal to 3, it comes back to life, otherwise it remains dead. That seems promising. So now we want to go up here and check count neighbors. No longer assume it works perfectly. So the neighbor counts is an empty array. Then rows is board.length, columns is board 0.length, so now we know the dimensions. It'd be probably quite nice to set this up initially, but that's a bit of a pain to do in JavaScript, so TypeScript, whatever language we're working in. So let I is equal to, so we're arranging over all of them, we're collecting a whole row. Now for J, and now neighbor count is currently 0. If we're out of bounds, do nothing. Otherwise, so here we're going to go from -1, 0, 1, -1, 0, 1. So that gives us, for this cell here, for example, we're looking at all the neighbors and itself. Check them all, do nothing. Otherwise, add. Because here 0 means dead, 1 means alive, we can just add that directly onto our neighbor count. Neighbor row.push neighbor count. Now because we counted ourselves, we're going to cut that off. And then we're going to push all of those onto the neighbor row, and then we end up with the final neighbor counts. Looks pretty good. Shall we give it a test? Let's see what the Oracle says. Oh no, cannot find name rows. Of course. Because we used them up here, didn't we? Well, we're going to need those again anyway. So, actually it's not worth it, is it? It's not worth it at all. We use them exactly once. Okay, this time assuming we've not done anything too stupid. Let's see what happens. Ah, that looks promising. What were those test cases? That was this guy, wasn't it? Yeah, that's that guy. So we're correctly producing that output. Let's have a go at the second one as well. So we want 1, 1, 1, 0. And we should end up with 1, 1, 1, 1. Yeah, it's always a bit terrifying. There we go. Completion day 1 day streak. Oh, lucky me. We were faster than 98% of TypeScript solutions apparently, and use less memory than half of them. Nice. Although apparently I've done this one in the past in Python. That's interesting. I don't remember doing this one in the past in Python. But hey, I can imagine we could tidy it up quite a lot nicer. This particular thing here would be much easier if we were to have comprehensions available to us, which Python provides. Alright, that wasn't too bad. Thank you very much for watching, and I will see you tomorrow. Bye. We've not done anything too stupid.